Hello everyone. In this video we will continue with to examine topic 12.1, the interaction of matter with radiation. Alright, so in the early 19th century, sort of in the time of the ultraviolet catastrophe, when there is this sort of fundamental tension in what we understood in our best physics with respect to blackbody radiation, there was at that time excellent, overwhelming evidence that light was an electromagnetic wave. And I can't overstate this evidence. So in addition to the wave phenomena that we've already seen, so diffraction, interference, etc., there was another piece of unbelievably convincing evidence that light was an electromagnetic wave, discovered sort of in the late 18th century. And that was that the speed of light, as measured, was related to the values of the constant epsilon naught and mu naught. In particular, c was equal to the square root of 1 over epsilon naught times mu naught, where epsilon naught and mu naught are the permittivity and permeability of free space for electric fields and magnetic fields, respectively. This tied the measured value of the speed of light to exactly constants having to do with how much that charges, whether moving or not, influence the space around them in the form of electric and magnetic fields. And not only that, this value was acquired through theory via Maxwell's equations, that is, through the differential equations that related the electric field to the magnetic field and vice versa. These are the real, sort of, quote-unquote, the real wave equations here. And using those equations, you can derive the speed of a wave of self-propagating electric and magnetic fields would be exactly the speed, and we verified it using experiments having to do with sort of interference. So, just unbelievably overwhelming evidence that light was an electromagnetic wave at this point. And so that's why when the photoelectric effect was discovered, it was discovered and characterized with surprising implications for this belief. This was discovered and characterized in a way that left no doubt that the theory that light was an electromagnetic wave had to be adjusted because the effect, when sort of fully understood, could not be explained on the theory that light was an electromagnetic wave. And in fact, the photoelectric effect led to the discovery of what was later called the photon, after the photoelectric effect. This idea that what light was fundamentally something like a particle in some ways, and inconsistent with it simply, purely being an electromagnetic wave. So given that, right, what is the photoelectric effect? And actually, it's quite straightforward to explain and define the effect itself. So here's what happens. The photoelectric effect is the emission of electrons when a material is exposed to electromagnetic radiation. So if you take UV or infrared or optical light of the appropriate sort, which we'll talk about later, and shine it on a metal, that light is absorbed and it knocks electrons off, and those electrons have some speed v. Those electrons that have absorbed the energy coming in from the light and are ejected from the metal itself are known as photoelectrons, which is not a special term for electrons, that's just a term for these particular electrons. They're just normal electrons that have been knocked off by that light. And the material is usually metal, so we're going to talk mostly about metals in this case. We're also, although this effect can be found for other wavelengths of light, it was primarily studied in the infrared, optical, and UV. And if you take a look at sort of how you might actually detect this, if you take sort of a charged zinc plate and shine ultraviolet radiation on it, you can actually knock electrons off the zinc plate, which can be shown via a gold leaf electroscope as demonstrated right here. That gold leaf will drop given the application of ultraviolet radiation to a negatively charged zinc plate. And quite straightforwardly, this just is the photoelectric effect. The experiment we're about to discuss with the photoelectric effect is much more complicated, but fundamentally, this is the effect. If you shine radiation on a metal, it will eject electrons, known as photoelectrons. And it's important to recognize that sort of for classical waves, you would expect the intensity to be proportional to the amplitude of that electromagnetic wave. And at this point, we would have no reason to believe that electromagnetic waves were any different. So what we're going to do is we're going to study sort of what actually happened, all right, using a careful experiment to the electrons, sort of what was their energy and what were their properties. When do we get electrons ejected and how many? And at this point, we're sort of expecting electromagnetic waves will be our, so we'll appeal to the theory of electromagnetic waves to explain the properties of those ejected electrons. And there's no reason to believe that they won't allow us to explain what is going on here. As it turns out, as you might guess, that will get a little bit more complicated in the next video.